Greetings everyone. In this presentation, I am going to talk about some trends in the testing of automated and highly autonomous vehicles. I am going to do this via giving you some definitions and examples of some buzzwords that are currently being thrown around in this field. The examples I am going to show you in this presentation will be mostly from our department. We will start from an engineering perspective. First, talking about simulation, computer simulation in the field of autonomous and highly automated vehicles. What do we test? How do we test them in this field? And then we will move on to more complex topics. We will see how we can connect different simulators to perform some cosimulations, and then we will see how we can connect real objects to our simulations to perform mixed reality and digital twin testing. I am also going to talk about the computer visualization counterpart of these topics, and I will give an outlook on virtual reality, the purpose of virtual reality in testing, and then the purpose of augmented reality in testing. So what's the purpose of simulation in autonomous vehicle testing? Simulation is cheaper, faster, and safer than performing real vehicle tests, especially when the development is in an earlier phase, when we already have some function, but we do not have the vehicle ready. Then we cannot do it with a real vehicle. We have to limit ourselves to simulations. Simulation can be much faster because we do not need the target hardware. We can run our simulations on a computer, which can be faster than our target hardware, and we can also run parallel simulations, which means we multiply the speed of our simulations. And of course they can be safer because we can generate corner cases which cannot really be reproduced or would be very dangerous to reproduce in reality. Near crash cases, or when the vehicle is about to slide, we would like to see how an autonomous function behaves in such situations. Those are also very hard to reproduce because we do not want a real driver to risk his life by going close to a truck at high speed or something like that. Another advantage of simulation is that tests can be automated and reproduced, so the results are reproducible. Simulation can be also used for data generation. Instead of using real vehicles on public roads to collect data to do measurements via their perception sensors, simulations can be run in realistic simulators where the simulation data can be logged, for example via virtual sensors, or other states of the vehicle can be logged. And also it's easier to define more exotic scenarios or cases because those are more interesting when you are trying to teach some machine learning or AI-based algorithm, which are pretty common in autonomous functions. In addition, most of the public road testing data is pretty useless because basically nothing happens. You just go straight on a highway and you collect a lot of kilometers and a lot of data, but basically nothing happens. There's no extra information for a machine learning based algorithm. Next, I will talk about what do we simulate, and first I will do it from a vehicle engineer perspective. Vehicle engineers have highly sophisticated simulator tools that have very accurate vehicle dynamics. They have sensor models, and there are also driving simulators, but these systems are all ego vehicle centric, and you have a very detailed model of the ego vehicle, and then you can add some environment and some other vehicles that are participating in some scenarios, but not in a highly detailed way. In this video, you can see the software IPG car maker in a scenario where the Zalazone test track is modeled and the vehicle is performing some tasks or maneuvers there. For example, you will see a pedestrian that basically it's a pedestrian dummy that goes in front of the vehicle, and the vehicle does an emergency brake. And you can also see the wheel forces next to the force vectors next to the wheels, which indicates that this software can simulate accurate vehicle dynamics, and basically that's what it is for. The model of the test track in CarMaker, but also in other software, for example, Virus, Priscan, also in Unity, Sumo, are available on GitHub. See the description below. Simulation can be also grasped from a traffic engineering perspective. It's a special and smaller field, but they are simulating on a much larger scale. Traffic engineers simulate networks to support intersection design or public transport planning, to develop different signal programs and calculate origin-destination matrices. So because it's such a large-scale simulation, the dynamics of individual vehicles are not that detailed. The next simulation is in Vissim, which is a microscopic traffic simulator, and you can see the 6th district of Budapest. It's around Octagon. It's modeled, as you can see, the graphics is not that good quality, and the vehicle dynamics are also not that good. So, for example, the wheels are not rotating, and lane changing looks weird. You can see that public transportation is modeled too. You can see the trams, the tram stops, and passengers boarding and alighting trams. The main purpose of this simulation is to see how traffic behaves in such a complex environment with traffic lights and intersections, and provide a tool to optimize such systems. The third point of view is from computer visualization. It has a very important purpose in the testing of automated vehicles. Using computer graphics in automotive development is not new. These are all used for 3D rendering of CAD and CAM models. They are also used in virtual showrooms, where you can see the vehicle photorealistically. Also, there are different vehicle simulators, test rigs, where the visualization part is also very important to create the immersion for the driver. Finally, and this is where it becomes very interesting for autonomous vehicle development, it can be used for simulating virtual perception sensors. In terms of camera systems, this is very simple, because you have some very photorealistic view in front of you, and that will be the image of the camera, and that you will use, for example, object detection or for some other algorithm. But you can also use it for radar and LiDAR simulation. These computer visualization tools are mostly based on game engines, for example, Unreal Engine or Unity. These are very general purpose, which means that you can develop whatever scenario you want. They are very flexible. So if you want, you can create your own vehicle dynamics inside the game engine. There are already such tools, for example, AirSim or Carla, which can be used for simulating perception layer sensors and teaching AI. In the next video, we use the game engine Unity to generate ground truth input data for a very accurate industrial radar model. Based on the raycast algorithm, we cast rays in each direction. Each ray is responsible for one radar beam, and we check the distance the ray travels, and we also calculate some radar cross-section value for that beam. And finally, we arrive at Cosimulation. So we talked about the automotive industry, who has very detailed but egocentric vehicles with accurate vehicle dynamics and sensor models. We have the computer visualization field that can create photorealistic images. And we have the transportation field that can create large-scale traffic scenarios. Previously, there was no transition between these fields because for vehicle manufacturers, it was enough to test their ego vehicles very accurately. But with connected and automated vehicles, it becomes more and more important to how to interface with the traffic network or other participants of traffic in a larger scale. And similarly, when we put different perception sensors on these vehicles, especially cameras, it will be easier to test with photorealistic images where the automotive manufacturers did not have that much know-how, so they had to take it from the computer visualization field. But of course, all of these software can do on its own these things. For example, these vehicle dynamic simulators have perception sensors, but they can also simulate some traffic, but not in such a detailed way as the others. So instead of some huge and complex simulator or simulation software, it's better to interface between these software, and this is how we get cosimulation. With such complex engineering systems such as autonomous vehicles, we need multidisciplinary solutions, so it's not possible to have just one simulator that can do all the tasks. So we simulate different components in different simulation software, and we do the interfacing between these software via TCP, IP, COM, or functional mockup interfaces, or we can have some cosimulation platform. So basically, cosimulation is when we have multiple simulators for different purposes and we run them together, and there is continuous data exchange between them. And the most important thing is the synchronization between these multiple software. It does not have to be in real time. It can be slower or faster, but they have to be in sync. This video shows a very simple example of cosimulation. Here, the traffic simulator Sumo is connected with the game engine Unity. The communication is only one way. Traffic simulator generates the vehicles and their positions based on some car following logic, and the purpose of Unity is only visualization because it can visualize much nicer or much photorealistically compared to Sumo, which is only 2D. And this project is available on GitHub. But you can also connect vehicle dynamic simulators with the visualization tool, or you can have large-scale traffic simulation in a sensor simulator tool. For example, you can connect pre-scan with Sumo through MATLAB. The possibilities are basically endless. You can just think of these connections and what can you do with connecting these different software. So you can just extrapolate from here. Think about it a little bit. Next, we will talk about different levels of testing. I think you are all familiar with these abbreviations. We have seal software in the loop, which was basically what we were talked about. It's only computer simulation with dedicated software. And then we have hardware in the loop, where we introduce a hardware into our simulation. It can be an ECU or a rapid prototyping hardware, so not necessarily the target ECU, but some real-time hardware. So it's one step closer to reality than only simulation. And next, a vehicle in the loop, where the hardware is the vehicle itself. The next question is its surroundings. It can be either on a test rig where the environment is virtual, or it can be on a real test track or on a public road. You have seen some videos on simulation, so I am not going to show it again for software in the loop, and I think hardware in the loop is not that interesting. So I will show you a video about vehicle in the loop. It was recently carried out at the Zalazon test track with a BMW M2, where a control algorithm that controls its wheels and its throttles and brakes. In this example, the goal is to keep the BMW drifting, and this is done via actuating the throttle and brake pedals, and also we have a steering wheel robot, and that actuates the steering wheel. That's the hardware that's in the loop. And the algorithm that we are testing is the control that keeps the car drifting. Vehicle in the loop testing is of course much more realistic than simulation, but it's also much more expensive, and there are corner cases but we have talked about that we cannot test with vehicle in the loop testing. And the next step, which I think you also heard a lot about, is this canary in the loop testing, which requires a proving ground. But once we have a proving ground, we can not only put the ego vehicle into the loop, but we can also put the whole scenario, so the test track and the objects on the test track, into the loop. We can control the whole simulation at once. And with the help of scenario in the loop and vehicle in the loop testing, we will introduce mixed reality and digital twin. And in this scenario in the loop example, we have the smart, that is the real vehicle, and we have its digital twin. So you can see that the two are moving in parallel, and if the real vehicle stops due to an obstacle, the simulated vehicle will also stop because the GPS position is communicated to the simulator. When we put a virtual obstacle in front of the virtual smart, the real smart, so both vehicles will stop, because we send back some virtual sensor data, virtual LiDAR data of the virtual vehicle that detects the virtual obstacle that only exists in virtuality, but we can send it back to the real smart, so that will stop too, because it thinks that there's a real obstacle in front of it, but it's only virtual. You can also see a pedestrian dummy that goes in front of the real car. It does not exist in the simulation, by the way, so it only exists, so it's only in reality, but it is controlled by the skill software, by the control software. So this is why we say it's a scenario in the loop, because we control the whole scenario, because if the real vehicle is at a given position, then we will launch this pedestrian dummy in such a way that it goes in front of the smart, so it forces it to stop. So in this slide we have these two definitions. So we have mixed reality, where some parts of the test is in reality and some parts are only simulation. For example, in the scenario in the loop video, you have seen that the pedestrian dummy is only in reality, but we also have a virtual dummy that virtual pedestrian that is only exist in virtuality. So they coexist in the simulation and they can interact with each other. And also we have digital twin. We have seen the digital twin of the smart. So we have the exact replica of the real object in the simulation, they move in parallel, they continuously communicate with each other. And the main advantage of this digital twin is that we can measure whatever we want on the virtual vehicle. For example, if it has some more sophisticated vehicle dynamics, then we can measure vehicle forces, while we cannot put all the sensors on the real vehicles. But because their positions are communicated to each other, they will act similarly, so the measurements can be accurate. In this very brief example, you can see the smart at the BME campus and its digital twin in the traffic simulator Sumo. The real smart communicates its position via GPS to the simulation. In addition, based on the position of the virtual target vehicle, the real smart adjusts its velocity, thus realizing a simple cruise control via a digital twin and mixed reality environment. The next two definitions are virtual reality, VR, where it is basically just a way of visualizing the simulation or the test. You need a special device, a VR headset, for example, but you can also do it via a smartphone which has a gyroscope, and use, for example, a Google Cardboard, where you just put your phone and strap it onto your head, and you are in virtual reality. Here we have a video. It does not look that good because it was recorded by an Oculus Rift, so it's a VR application, and it's a virtual test drive on the smart city part of the Zalazone test track. This that you can see is also available in the Play Store. You can download it as an application and install it to your phone, and you can enjoy it wherever you would like to. And finally, augmented reality, where you can see both the virtual objects and you can also see the real objects, and these are rendered together. Unfortunately, we cannot give you an example that was carried out by us, but here you can see a video from Volvo that performs some testing with augmented reality. In this video, what you can see is that they have this augmented reality headset, and occasionally they just show some virtual obstacles to the driver and see how the driver reacts to these obstacles. It is safer because you do not have to send out a real moose in front of the car, but only a virtual one. Okay, thank you for your attention for this presentation. And if you found these topics interesting, you can check our Facebook page, BME Automated Drive, or our YouTube channel with the same name. And if you happen to publish something that is related to these topics, then please cite some of our work. Thank you for your attention again.